Alright, in this video we're going to learn how to solve ramp problems in forces, and it's going to be the exact same thing we have been doing, just with a little twist. So here's a good sample problem. If we have a 20 kilogram brick that's on a ramp, okay, and it tells us the angle of the ramp is 35 degrees with respect to the horizon, and the coefficient of friction on the ramp is 0.26, and they want us to figure out the acceleration of the block. Eventually, we'll also figure out how fast it's going at the end of the ramp. So we're going to approach this problem just like we do all other problems, and we're going to simply start by doing what we always do, which is step number 1, draw a free body diagram. So let's identify all the forces on the block. We know that there's, of course, the weight downwards, or the force of gravity downwards, which I'm labeling as W for weight. Okay, and then we also know that there's the normal force. Normal force is always, again, perpendicular to the surface. So if this is the ramp, normal force is perpendicular to that surface. We know that there's friction. I know that friction is not negligible because it gave us a coefficient. So I know there's friction going up along the surface of the ramp. And these are our different forces. Okay, and this is it. Some people like to think that there's a force pushing it down the ramp, but there is none. Okay. There's nothing pushing this object at all, so that's just a made-up force. There's no force there. The net force, however, will be downwards, but we never draw that on our free body diagram. All right, next thing we do is we establish our coordinate system. I'm going to say down is positive, and to the left is also positive. I'm going to say that because the block is moving down and to the left. Next thing we need to do, right, is to split up our diagonals. This is just the standard steps we always follow, right? So draw a free body diagram, and then we find our diagonal forces and we split them up. We want to split them up because it's hard to write an equation to relate other forces to weight when they're not even in the same direction. So I want to identify my diagonal forces. That includes no force, and it includes the force of friction. Also, it includes not just the normal force and force of friction, but the acceleration, right? Because the acceleration, it's going down the ramp as well. The block is actually sliding diagonally. So I would actually need to split up this as well, because if you were to write an equation by relating the horizontal forces together, right? Let's say one of these forces might be bigger than the other one, which it is. So horizontal part of normal force is bigger than the horizontal part of friction. The sum of these two forces, or normal force minus friction, minus because they're opposite directions, right? So normal force minus friction would be the net force and would equal ma. Well, which part of A? It wouldn't be the diagonal. It would just be the horizontal component of A. So you would have two different accelerations, or two components of the same diagonal acceleration. This looks torturous. This sucks. There's no way I want to do this. Way too much work. Okay, and I don't want to do this. So I have, out of 4 vectors, I have to split up 3 of them. Instead, there's got to be a faster way, and there is. And this is the trick to solving all ramp problems. So to better go over why, or what to do to make this work and make this a little bit simpler, let's examine what we're trying to do right now. Currently, we have a coordinate system that looks like this, where horizontal is, well, horizontal, and vertical is, well, vertical. So this is diagonal, the normal force is diagonal, friction is diagonal, and acceleration down the ramp is also diagonal. So that's not very helpful. It's just too many diagonals, right? So the simple way you can solve this is by simply rotating your coordinate system, so that instead of looking at it so that this way is horizontal, let's make horizontal be along the surface of the ramp. Vertical is now perpendicular to the ramp. What that means is that friction, which used to be a diagonal force, is now a horizontal force. Normal force, which used to be a diagonal force, is now a vertical force. Acceleration, which used to be a diagonal vector, is now also horizontal. And weight is the only force that is diagonal. So when I split up my forces, instead of splitting up, and vectors, instead of splitting up three things, two forces and an acceleration. I just have to split one, weight. However, it's going to be split differently, right? The new vertical is this way and the new horizontal is this way. So weight is my new diagonal. And if I take a look and actually draw in the components here, so this component is the vertical component, this component is the horizontal component. All I need to do now is to split up this weight into two components that I can do something with. So in order to do that, though, I need to actually find the length of this side and the length of this side. Well, to do that, I need an angle. I might be able to know this side, the hypotenuse, is the weight, and I probably will be able to calculate that from the information since they gave me the mass. But what I need to do is I need to figure out this side, which I need an angle. I have an angle over here, that's the angle of the ramp, but it's not in my triangle. So the question is which one of these two angles in my triangle is the same as the one on the ramp over here? So I need to do a little bit of geometry to figure that out. And you have to always think to make sure that you put the angle in the right spot. If not, everything will be backwards and wrong. So let's take a look. Let's look for some simple geometric shapes. I can see that this triangle right here involved with the ramp and this line here is a right triangle where this is 35, that's 90, and so therefore this one must be the complementary angle of 35 degrees, or in other words, this angle is 55 degrees. You'll also notice that the angle between here and here, as highlighted, should be a 90-degree angle as well, right? Because this is the surface. Here's normal, right, to the surface, so this is by definition perpendicular. So this angle and this angle together should add up to 90, which means this 55-degree angle and this angle is also complementary. So if this is 55, that angle right there must be 35. So we have identified now which angle in this triangle is the 35-degree angle, and we can now actually split this weight up into its horizontal component this way and its vertical component this way. All right, so I've split it up. Now we've been doing this for a while now, so hopefully you know where this comes from, but we're just going to jump through it quickly. If this is your angle theta, right, and this is the adjacent side, I can do trig and I can find out that the length of this side will equal the hypotenuse, which is the weight, times cosine of the angle here, and that will be equal to this length. Similarly, this side is weight times the sine of the angle. And then once I figure that out, I can now create what I like to call a working free body diagram. This free body diagram here, without the dotted line stuff, is my original unadulterated free body diagram. If ever on a test they say draw a free body diagram, this is what you draw. So just to keep track of this, I'm just going to put this off to the side, and this is my original free body diagram. Now I'm going to create a working free body diagram, something that is useful, that I can actually use to solve or make some equations and solve. So I'm going to get rid of this force here and replace it with one this way, weight cosine theta, and one this way, because these two together add up to the one down. So I'm just going to simply replace those, and hey, I'm going to move the force that was down here. I'm just going to move it up here just because it looks nicer and it looks like it makes more sense to me that way. So now from here I can see, oh, this force and this force, right? I can relate these forces together, and these forces I can relate together. This is starting to look like just a normal, regular problem that we normally solve with forces, and I can handle it just like any other problem. So again, now that I've got my diagram all set up, again, I'm looking for the acceleration. So let's go about making an equation to find the acceleration. All right, so again, I'm going to create an equation for this. Let's move our diagrams off to the side and create an equation for acceleration. Now, it's accelerating in the horizontal direction, the x direction, okay? And we know that weight, sine theta, or the component of weight that's along the ramp, must therefore be bigger than friction if it's accelerating down the ramp. So I'm going to write an equation in the x direction using these two forces, okay? I know that the difference between them will be the net force, and I know that the net force is equal to ma. So the sum of all forces, or net force, should equal ma in the horizontal direction. I'm going to replace the sum of all forces with an expression here represented from all the forces in the horizontal direction. And that expression will be, to represent the sum of all forces, will be weight sine theta minus friction. Okay, and I'll come up with this equation here. So now we have a working equation that we can use to solve. All I need now is to find A. If I know mass and friction and weight and the angle, I've got my acceleration. Oftentimes, in a lot of these problems, we also need a second equation, one from the vertical direction, the y direction. So I'm going to go ahead and calculate that, or write an equation in that direction as well, just for the sake of that, it's usually useful. So again, we're going to do F net, or sum of all forces, is equal to mass times acceleration, this time in the vertical direction. And so we take all the forces in the vertical direction, write an equation. That'll be normal force minus weight cosine theta, or vice versa, the other way around. Should equal mass times acceleration in the vertical direction. However, it's not accelerating this way, right? Remember, the ramp is like this. The block's sitting there. It's going to go down the ramp, but it's not going to like jump off the ramp or go into the ramp. So it's not accelerating perpendicular to the ramp. It's only accelerating parallel to the ramp. So acceleration in the vertical direction is 0. So this simplifies a little bit more. 0 times any number, mass, is equal to 0 as well. And I can simplify this one last time. And here are two equations, one written in the vertical direction and one written in the y direction. So this force up equals this force down, and these two, the difference, will equal mass times acceleration. These are my two equations that I'm going to use now to solve for acceleration. All right, so now that I have the information, I just need to start plugging in numbers and solving. So remember, this is the given information they gave me. I know the acceleration in the y direction is 0. I'm looking for the acceleration in the x direction. I know the coefficient of friction is 0.26, the angle, and I know the mass. So mass, check. I'm looking for acceleration. Friction, don't know. Angle, check. I know it. Weight is not also on my list. But I can figure out friction and weight because I have equations for both of those, right? We've already derived the equation for weight and for friction. We know that weight is equal to mass times the gravitational field strength, which on Earth is 9.81. So we'll do a quick substitution. Where weight used to be, we'll just put in mg, okay? And then we say, okay, well, friction, I know kinetic friction, there's an equation that we've used, or derived in the past, which is that friction is equal to the coefficient of friction times its normal force. So we can do another quick substitution and substitute coefficient of friction times normal force in place of where friction used to be. Now, if you know the numbers, you can also plug in some numbers ahead of time. I just like to do this all with variables first before I solve anything. Okay, so now let's see here. Let's go through and see what we know so far. Mass, I know it. G, I know it. It's 9.81. Theta, I know it. Coefficient of friction, I know it. This is looking good. Normal force, don't know it. Mass, know it. And I'm looking for acceleration. Great, so we're almost there. I just need to now know the normal force. Well, there are no equations for normal force. So how can I figure it out? Well, by looking at my free body diagram and looking at this equation over here, right? I already determined that the force normal was equal to the component of weight perpendicular to the surface, or weight cosine theta equaled the normal force. So let's make another substitution. Take this, which is equal to normal force, and plug it in for a normal force. Okay, and it simplifies to this. Again, here's another weight, so let's make another quick substitution, replacing it with mg. And boy, this is starting to look ugly, but let's take a look and see what we got. We have mass is times the gravitational field strength. So we know mass, we know gravitational field strength, we know theta, we know coefficient of friction, we know mass, we know g, we know theta, we know mass. Hey, and we're looking for acceleration. Great, now we have all the information we need, and we can just plug in our numbers and solve. We've combined multiple equations together to make one that will work. I can actually simplify this one more step, which is kind of useful. if I divide both sides by mass, let's see what happens. So the mass, as you can see, cancels out. So there's mass here, there's mass in this term, there's mass in this term, and mass just, poof, disappears. That's really useful. In fact, that has significant meaning. If mass cancels out, that means I could have put a 50 kilogram block on, or a 200 million kilogram block on, or a 0.00001 kilogram block on this ramp, and it would still have the same acceleration because mass disappears. The answer is independent of mass. I didn't even need to tell the equation the number for mass. It's independent, so it doesn't really matter. So the answer is the same regardless. So this is now my answer, and I just need to plug in numbers and solve. Oh, and apparently that answer is 3.54 meters per second every single second. All right, and last but not least, we got to just make sure that our answer makes sense. So again, we said the acceleration turned out to be about 3.54 meters per second every single second. So we're just going to stop and think about that and ask ourselves, wait a second, does that make sense? Well, if the ramp was at a 90-degree angle, that means it's pretty much at free fall, right? What would the acceleration be? Well, at most, it would be the acceleration of 9.81, equal to the gravitational field strength. Well, if I already know that, is an acceleration of 3.54 seem feasible for an angle of this magnitude? It seems feasible. It's all right. It's within our realm of possibility. So the answer kind of makes sense, and it's trustworthy.